Good afternoon, everyone. I'm Ankur, an investment director with TDK Ventures focused on AI, compute, and connectivity, and excited to welcome you all to this yet another exciting session, this time on the future of AI computing and connectivity. Could I request all of you to maybe take a minute to introduce yourselves and the company you are building or part of?
Yes, I'm Shrijeet. I was the CTO, co-founder of a company called Enfabrica. But I've had a very interesting life, I would say, a very lucky life. I started at a company called Silicon Graphics, building something that today is called the GPU, which some of you might have heard of. I spent after that a bunch of time at a company called Cisco, or actually a company that got acquired by Cisco, building the world's first SmartNIC. And after that, I was VP engineering of a company called Cumulus Networks, which is now a part of NVIDIA as well, which was ushering in the era of open computing and open networking. And the last thing that I did, which sort of was the culmination of everything else, was Enfabrica, which is a chip that does scale-up, scale-out computing and sort of addresses the next generation of what AI infrastructure needs from a compute connectivity perspective.
Hi, Drew Perkins. I know many of you, and many of you know me, I suppose. I've got a long history in networking, in particular since back to 1981. I was involved in the very founding of the internet. The spec for how you put a TCP/IP packet on Ethernet acknowledges my help. I will argue that I actually was working on the very first SmartNIC, because in 1986, I was doing a master's project at CMU, building the first SmartNIC.
This panel is getting interesting already.
Virtualization wasn't there yet, but okay.
In 1987, as far as I know, I tried to start unsuccessfully the first Ethernet switch company and designed the first Ethernet switch. But I've been at 4 Systems as a leader. I've helped lead the OF, started Lightmatter, optical switching, Infinera, co-founder of Infinera. And I would have loved to be on the last panel too, because I was a founder of Mojo Vision, developed the world's first augmented reality contact lenses, and we really made them work, and I've worn them on my own eye. So that was fun. But now I'm building Eridu AI, where I'm very interested in making GPUs a lot more efficient and building large data centers that are very efficient and the networking for them. Thanks.
Yeah. Thank you. My name's Ritesh Jain. Head of engineering at Lightmatter. We're a silicon photonics startup, I should say. Well, probably the largest silicon photonics startup. We're based out of Mountain View in California. And before I talk about Lightmatter, maybe I'll just talk about where I spent most of my life, about 20-some years at Intel. Last role there was vice president of hardware engineering, focused on data center products. So through my time at Intel, I brought about 10 generations of Xeons into the market. Know a lot about data centers, of course, and what it takes to essentially deploy products into data centers. At Lightmatter, we're focused on 2 aspects. We fundamentally believe silicon photonics is the path forward for both interconnect and for computing. Our initial focus was on computing, but more recently we've made the pivot to focus on interconnect first. And we have 2 products there. One is NVICE, which is the computing aspect, and then there's Passage, which is our product for interconnects.
Yeah, I'm Rabin Sugumar. I'm the CEO and co-founder of Akeana. Akeana does RISC-V compute IP. Most of our customers are in a variety of AI spaces. Prior to Akeana, I was the lead architect on the Thunder X2 line of ARM servers, which are the first generation of ARM servers that went into the supercomputer top 500 and Azure and other places. And I've spent many years in big companies doing server-type CPUs. So I was an architect at Sun Microsystems, and before that at Cray Computing doing high-performance computers. So looking forward to the conversation today.
Great. Let's dive right in. Let's start with the computing bottleneck. The GPUs have dominated the AI inference and training market for the last few years, but lately we have seen an explosion of all kinds of different accelerators, ASICs, and different architectures. So Rabin, I want to start with you. Could you talk about the RISC-V architecture and the IP that you are creating, and what kind of challenges are you going after, and what kind of opportunities do you see in that market?
So, if you look at, we are in the very early stages of the AI revolution, right? And the early stages, it tends to be a little bit brute force. And right now, a lot of solutions tend to be brute force, right? So, if you ask ChatGPT, where do I go for coffee? All 600 billion parameters or 1 trillion parameters are fetched, and the whole compute goes through, right? And so what happens as an area matures is CPUs become more important because you really want intelligent decisions made upfront so you don't burn all that power and you don't use all that memory bandwidth and CPU compute to do things that you don't really need to do. For instance, right, you could have separate engines for simple questions. You could store, because 90% of the questions are probably repeat questions. So you could store, and I'm sure ChatGPT is doing all these optimizations. But as they are done, CPUs become more important. And what we are finding is RISC-V is the CPU of the AI compute, right? Because it's the only top-of-the-line architecture that is open. And there is definitely a desire not to get stuck with another proprietary architecture and then have to pay the tax for that proprietary architecture. And then there are other aspects too. There is sovereign compute, so there are different geopolitical areas, and people want to own their own compute ecosystem. But beyond those kinds of considerations, right, the thing that really sets RISC-V apart is the customization. So if you look at AI, AI use cases don't need all the features that a high-end CPU has. And if you go to any of the other vendors, you get one size fits all. You have to get a CPU that does everything. And so RISC-V really stands out in how it can customize for different use cases. So in Akeana, we have built an extremely customizable portfolio of CPU cores. So you can do the traditional server type cores from us, and that does have a use case even in AI. But we can also do these highly customized cores without many of the features that the high-end server cores have that are focused on specific AI compute solutions. And that's what we are talking with a lot of customers about.
Got it. And Ritesh, Lightmatter is taking a very unique approach with light instead of electrons. So help us understand what can photons do that electrons cannot? And maybe also talk about the timing aspect of optical computing.
Okay. There are two fundamental sort of laws that governed, computing for a very long time, multiple decades: Dennard scaling and Moore's law. It hurts me personally. I feel the pain, to even say this, but they're either dead or they've slowed down dramatically to the point where a different paradigm shift is required. A very different approach is required. And we've seen the industry make that pivot. We've seen the industry move to more of a heterogeneous integration, a chiplet-based approach, smaller tiles of silicon put together on the substrate. But then now we're dealing with a different kind of problem, which is essentially how do you now move data? How do you now move compute across those tiles efficiently? And that's where I think photonics comes into play as well. It takes a lot less energy to move a photon than it does to move an electron, in my opinion. And so from that perspective, whether it's computing or whether it's for interconnect, we definitely see the place for optical computing and interconnect now. Added to the two laws that have either slowed down or gone away, we've seen this massive shift in the ecosystem around AI. It's one word that everyone talks about, or it's two letters that everyone talks about. And that's brought a need for essentially what I call single brain data centers. The entire data center now it's not one or two racks of compute. It's hundreds of racks that have to now operate as a single unit of compute. And to be able to get to that level of connectivity and compute, it takes something different from traditional copper. And so that's where, at Lightmatter, we've been focused on essentially enabling, like I said early on, initial focus was on compute, but then we realized that we probably need to solve the interconnect barrier first before we pivot to compute, and that's where we've been focused on. On the compute side, what we've done is we built an AI accelerator, which has about 65,536, I think it's 2 to the power of 16. compute engines in a accelerator chip, all based out of light. Only use light to do all the computing. And we've deployed it across several inference type workloads. And actually, there's more to be said about that. I refer you to a Nature publication that was recently come out in the month of March, I believe, on the area of optical compute. But there's a lot to talk about the interconnect as well, but I'll pause.
Yeah,
Turn it over.
but from a timing standpoint, when do you think it'll become mainstream?
Optical
Is
compute,
it like
I
5
think,
years away? More?
certainly more.
Yeah.
More. From an optical compute perspective, I think we're still a ways out. Yeah.
Got it. Drew, from your vantage point, optimizing AI infrastructure, what kind of inefficiencies or bottlenecks have you come across in real-world AI implementations?
Well, I think the problems Lightmatter is trying to address are certainly there, just the energy it takes to move information back and forth, but also to switch it. And I think that the moving data in and out of these GPUs is horribly inefficient, and the differences we see between memory performance and scale up and scale out and all these things. I think that we don't yet know what the proper size of a scale up domain is, and it's rather limited today. It's been growing from 8 to 72 to hundreds, but nobody knows what the best size might be, or where performance improvements can stop improving dramatically. So I think these are all really interesting questions to explore and opportunities for improvement of AI data center performance, cost, efficiency, et cetera.
Yep. Shrijeet, stepping back, does this compute bottleneck become smaller over time or becomes more prominent, bigger over time?
I think the answer to that is it becomes more prominent. But actually, before we talk about it, before we classify it as a bottleneck, right? I think a big problem with the general approach to AI is that everybody approaches it as if it's a 2-year-old problem or a 3-year-old problem, and the solutions we're talking about have never existed or have never been contemplated. If you go back to the late 90s, computers were refrigerator-sized systems or room-sized systems, and it was all vertically integrated. You go into the 2000s, and everything was about 2-socket systems that were connected with networks because problems fit inside 2 sockets. The 2-socket had become big enough to encompass the problem, right? And that's where it stayed till, I would say, the late, maybe 2017, 2018 timeframe. And then the world suddenly realized, no, that's not good enough. Let's switch it back around. Let's simplify the problem itself, make it vector computing, thus the rise of GPUs. And by building these vector processors, which showed you a 1000x, 2000x jump, and taking away the 2-socket form factor, you could again reopen, or the floodgates could be opened in the short term. That's the state of the art today, right? But if you look at something like DeepSeek, what DeepSeek did to the world, it basically said in the absolute short duration, better algorithms, better optimization gives you a 6x, 10x improvement. Does that change the long-term arc? No. The long-term arc is better power management, more compute, better context, AI, right? That's the long-term arc. It was always the long-term arc, if you think about it. It's just that you couldn't call it AI when computers were generating trajectories of a projectile, right? It wasn't AI. Today it is. But it's the same fundamental structure. So what is, to answer, okay, maybe to get back to your question, I think the compute problem was never a compute problem. It was always a memory problem. Because building logic, building processors, and I actually disagree, the processor actually ultimately becomes less relevant than the system you put it in, right? Because the system becomes a corollary or an indicator of how much memory and how much context you can have for that compute task. And exchanging memory has always been the fundamental problem. Like if you think about networking from the earliest days, it was always about moving data to where compute could actually do something with it. And Enfabrica's entire point was, instead of trying to fit networking into these sort of neat bundles of scale up and scale out and so on and so forth, what if you reimagined it in terms of how do you expand memory? How do you make memory available to compute fast? And how do you define it in terms of, AI calls it collectives, which is shapes and constructs which are tuned for the compute that the data is needed for.
Yep.
So the answer to your question, therefore, specifically is compute demand keeps growing, but the problem that it'll run into is how can you get the memory more efficiently? And we try to solve that problem first.
Got it. Got it. So you've already crossed over from compute to connectivity. So let's talk about connectivity now. Anything you want to add around Enfabrica?
No, actually, I think the biggest problems in connectivity today are physics, right? So I'll shove it back. And
let's go back to
the people who are
Ritesh
solving the physics problem.
Yeah, let's talk about Lightmatter's approach to optical interconnects using photonics. Maybe touch upon a little bit more details on that.
Sure. Photonics is not new to the data center. Let's start there, right? We do have optical transceivers today that are used pretty abundantly in the data center deployment. The problem with those is it's not about reach. Sure, you can still, once you get into the photonics space, you can go across multiple kilometers. The problem is about power, and how do you increase the radix? How do you make sure that you now have all the GPUs or any compute device talk to multiple compute devices at the same time? With traditional optical transceivers or pluggables, as we like to call them, you're talking about energy efficiency in the terms as measured by picojoules per bit. You're talking about anywhere from 18 to 20 picojoules per bit. And good portion of that power is really burnt in driving data from the compute or memory cluster all the way out to the edge of the board or the back plane of the rack. As we start to do more and more of what we would like to call 3D co-packaged optics, essentially now integrating optics directly underneath the compute device. You've now moved that power, or you've dropped that power from about, like I said, 19 to 20 picojoule per bit, down to about 3 to 5 picojoule per bit. That's a huge improvement in terms of the overall power efficiency. And we're not talking about saving the planet, or maybe that's where we should focus on, is how do we save the planet by reducing the power footprint. But to a large extent, how we see it is essentially also unlocking up to 4 times more compute for per gigawatt of deployment from a GPU or a CPU perspective. So that's sort of where we're focused on. And fundamentally, when we look at silicon photonics, to be able to do that 3D integration, there are some very fundamental changes that are required in terms of how we approach it. Devices today that are used for modulation in the optical transceivers are no longer valid because they are in the order of millimeters in terms of size. But to be able to get them directly underneath a dense area of compute, we need to bring those down to about microns, and that's where micro-ring modulators come into play as well. We've embraced the MRMs. We call them MRMs, and we've embraced MRMs just like other large companies like NVIDIA and even TSMC have essentially enabled MRMs as the choice of modulation technology. But MRMs have the problem of real-life problems like thermal stability, or how do we ensure that these rings remain stable through the temperature escalations that happen or the temperature variance that happen in real-life compute environment? How do you ensure that we can maintain light polarization of light when it comes to vibrations, when it comes to lightning strikes in data centers, and so on? So these are all real-life problems that we're solving at Lightmatter. I'll pause. I'm back there.
Let's bring Drew and Rabin into the conversation as well. Drew, what's your take on how is this compute innovation and fabric innovation going to co-evolve over the next couple of years?
I'm going to be very curious to see how that happens over the next couple of years. Frankly, I think there's an awful lot of competing technologies and companies that it's kind of hard to tell exactly how, whether 3D integrated silicon photonics is going to win, or frankly, what hasn't been mentioned, micro-LED technology, for instance, from companies like Mojo Vision and others. I'm kind of a big fan of that being the approach to get to tenths of a picojoule per bit and not single-digit picojoules per bit. But we'll see. There's more time necessary for that to happen. But I think it's very exciting that there are so many companies competing in silicon photonics, hell, indium phosphide, like Infinera/Nokia now, micro LEDs, gallium nitride, and new terahertz communication. I think there's a lot of interesting things that could happen over the next couple of years as we see it playing out. And then it's going to be very interesting to see how all this is switched appropriately for scale-up switching, scale-out switching, and if there ends up, in fact, being a difference between the two. At the end of the day, we've seen last week the emergence of Ethernet for scale-up networking. Over the last 45 years almost since that I've been in this industry, we've seen Ethernet win in every single category, and I think there's a pretty good chance that's what happens.
That one I agree with, yeah.
We'll see. NVIDIA has something to say about that. It doesn't necessarily, well, they were part of ESUN actually, so maybe it's an early indication.
And AMD too, interestingly.
And AMD as well, yeah. So,
with all these technologies, it's great time to be an investor. Rabin, what's your take on this interconnect innovation, fabric innovation over the next couple of years?
So one thing to respond to Shrijeet, right? I mean, it's like when you say compute, right, there is maybe a tendency to think about the arithmetic unit, which is really a small part of the CPU, right? A lot of the CPU goes into caches. I mean, how do you have more outstanding requests? In Akeana, for instance, we support threading, so we can have lots of threads moving data. So it's all a key part of compute, right? The arithmetic is a small part of it.
No, but I wasn't implying that. My point was that ultimately, I think, which is what Drew was also hinting at, ultimately, it's a macro problem, right? The micro problem is required, but if micro was the thing, we would all be using computers built by digital technologies, and alpha would be running everywhere, right? Because at its time, it was unbeatable, but it never was able to really solve complex problems because ultimately systems that were built around it weren't that great.
So in terms of, the data movement part itself, right? So the CPU is a little bit removed. So that is like, the memory, and then there is storage, and then there is other computers, and how do you communicate? So networking is a little bit more on how computers communicate with each other, right? Whereas the CPU is a little bit more focused on how do we get data from memory and process it, right? And in AI, while definitely the networking problem is also super important, because for scale out, the compute problem of, you have data in memory and you are computing on it to figure out answers to AI questions is, I would argue, the more fundamental question right now. Especially, in the data center, scale out is a little bit more important, but in many of the embedded use cases, right, special purpose use cases, most of the AI compute is within a device, right? The data movement is super important even within the device. The parameters and the weight storage themselves is just so big that you cannot really hold it in cache. And so a lot of our focus is in how we move data efficiently. So one of the ideas that we are pursuing, as I said, is threading. NVIDIA does a lot of threading, but in the context of RISC-V, we do a lot of threading as well. So we have lots of context outstanding, and we can intelligently move data from memory into the CPU to do the compute.
So the message is loud and clear. Without efficient data movement, compute alone cannot carry us forward. Great. Let's go to the 100x theme and ask each of the panelists, what's 100x metric, that you are trying to optimize for? What's your North Star metric?
The first is actually data movement, because I think, and that's what Enfabrica did, right? So if you think of the context, and even to respond to the ESUN and similar technologies, right? At the end of the day, all of these new things are calling themselves Ethernet, but they're actually reinventing Ethernet. It's got very little to do with core Ethernet, because fundamentally what has become clear is that communication efficiency, as opposed to interoperability, is now more important for compute efficiency, because data movement overheads are expensive. Everything else is sort of irrelevant. Ethernet PHYs are used by everybody. So it's not like they're not Ethernet in some sense. But what is structurally then important, once that level, field becomes level, is how efficiently can you move the data. So to the point about getting data from your highest tier, let's say remote memory, which is running on a disk somewhere, into your L1 cache efficiently in such a way that your processor has to spend no cycles trying to reformat it such that it can use it. So I'll give you an example. Tensors are dense, sometimes gigabyte-sized blocks of memory. Storing it on disk that way is terrible. On disk, you want to sparsify it. You want to distribute it as much as possible. But when you want to compute it, you want it to come in a dense format. If you spend your compute densifying it, you've done the wrong thing. That's actually literally the definition of what Enfabrica did, right? And so if you think of how this goes forward, like I was saying, on its current track, every component is getting 100x better on its own. You don't have to do much. The system, however, is not. So it is data movement that will fundamentally change the way you can make systems more efficient. And the second part will be the power that goes with it, the thing that we talked about. Because, again, doing this is possible today. But if compute grows and contexts grow at the current rate, which is 1000x, power has to catch up. So otherwise, you will run out of the earth.
I'm not sure what else I can add to that. It really comes down to power to move data. But
that was a catch-all answer. How about radix, bandwidth? What are you trying to optimize as a 100x metric?
I typically, things come down to economics, though, CapEx and OpEx. Although in the current day and age, I think it comes down to how fast can you build. And the application need here is so vast that practically infinite. Who doesn't need more intelligence? I'd love a lot more intelligence myself. So, the faster we can build intelligence and make it abundance as we move to this new age of abundance of intelligence, the best. So, can we develop this new technologies in a way that is prepped immediately and can be done on high volume manufacturing as we understand it today? And deliver to market incredibly fast to be able to build economically very quickly. That's another huge piece of the puzzle.
Yeah, I fully agree with everything that Drew and Shrijeet have shared. I mean, it's hard to optimize for just one vector and assume that you can it'll get deployable or buildable or even usable. I mean, you talk about bandwidth. I think we're seeing essentially bandwidth scaling 100x. To the point where what we have demonstrated is actually about a 50 terabits per second of bandwidth in a single reticle of silicon, or less than a single reticle of silicon. So from that perspective, bandwidth density is absolutely essential. But if we do it at the expense of power or to a point where it now can be deployed at scale, it's of no use. So all of these vectors are super important: bandwidth density, power efficiency, radix. They're all critical vectors that we optimize for. And then lastly, I think, as Drew put it as well, manufacturability. Being able to leverage existing processes in the ecosystem is absolutely essential. If we try to go down a path that requires now a dramatic change in the entire flow of, let's just say, how foundries operate or OSATs and ODMs operate, it's very unlikely that it can get adopted into large-scale data centers.
Rabin, you have a different point of view.
Not different. I mean, I think it goes,
no.
but I would say, we are focused more on performance per watt. I mean, I think power is definitely a limiting factor for AI right now. Yeah, I mean, it's just the build-out of power for all these data centers is just, I don't know how long we can sustain it. And so we do believe, as I was saying earlier, that compute is a big part of solving the problem. I mean, it's really algorithms, right? But you essentially have to get smarter about what computation you do. And that comes back to the CPU problem, but also algorithms and how we develop the algorithms. The other one that we are focusing on is specialization. The 1 trillion parameter LLM is not necessarily the solution for all verticals. And so we are working towards different verticals, different embedded spaces with their own AI use cases, and how do we most efficiently solve those problems. And if we solve a problem efficiently there, where we don't have to go to the central LLM, that's a huge saving in power.
Okay. So I want to end on a forward-looking note. It's roll forward 5 years, it's 2030. What's your one big bold prediction about what's going to change from now until 2030? in AI infrastructure?
Oh, infrastructure. I was going to say somebody's found a cure to some cancer.
Yeah. More important, but not relevant for this conversation.
I think if AI, I think we've actually already said that. Like if AI stays on its current track, then something has had to have shifted dramatically in power. Even in this panel, you're seeing the perspective of everything from edge and small to data center and large. But the fundamental common theme is power efficiency, right? Like it can't stay where it is.
Yeah. Okay. Drew, anything other than power?
Well, it does come out down to power and power density. I think another interesting thing that's going to be exciting to watch is, do we see the continued shrinking of things into, a single black hole of computing, where we've got gigawatts going into something that's a square millimeter, cubic millimeter, or do we see the proper or good use of optics to be able to spread things out and actually make it less dense and more sparse?
I'd say, I think in the next 5 years or so, we're going to see large-scale deployment of silicon photonics in hyperscale or type data center applications. But it's not going to be easy because in order to be able to do that, we have to actually demonstrate the ability to, whether it's reliability, whether it's deployments, we talk about fit rates, failure in time. We have to be able to demonstrate that, silicon photonic solutions are reliable because when they get deployed in a data center, especially with a hyperscaler, we're not talking about a few thousand units. We're talking about millions or tens of millions of these units that need to get deployed. And so failure rates are very, very critical. And that's sort of how we are approaching the problem as well. I like to use the term rings to racks. We use micro-ring resonators. And we focus on actually ensuring that those rings survive in the racks at the data center. So very exciting time. I think we'll see photonics go mainstream in the next 5 years.
That's great. Rabin?
So I would say maybe there's one question and one prediction, right? So the question is, what happens to AI in the next 5 years? It does feel to me like it's plateauing out. All the information in the internet has already been used to train these models. What more is there? So there is a question of, is AI going to get dramatically better over the next 5 years? Or are we going to see LLM performance kind of plateau out, right? The prediction would be increasing deployment of large-scale LLMs and similar technology in smaller form factors, embedded or laptop or tabletop. I mean, the NVIDIA DGX Spark is really interesting. I mean, in this fairly small form factor, NVIDIA has managed to pack a lot of compute. And we expect that to continue, where in these smaller form factors, a lot of interesting AI technology can be packed. And once you have that in these small form factors, the use cases proliferate. So robotics and other embedded use cases of AI will likely become a lot more prevalent.
Great. Thank you. Let's open it up to the audience. We have 7 minutes.
Thank you very much for a fascinating presentation. My question is more towards the optical compute ecosystem. Is that industry mature, and is this a necessary path to success towards quantum optical crypto systems or quantum systems that are being built that also need similar components? My feeling is that the ecosystem is not robust enough to build out, scale up. Is that true, or am I have a wrong understanding?
I can take a stab at it and love to get the other perspectives as well. I think there's still time from an optical compute perspective. And I do believe it is essentially a step required to get to quantum. But I think what we're seeing is the ecosystem essentially sort of laying the foundation for it now with the pivot to essentially unblocking the data movement or the interconnect bottleneck that we have. Because in order to be able to, we've seen compute grow at an exponential rate. Quantum will do that. Optical compute will do that as well. But to be able to truly unblock or take advantage of that compute scale up and the memory that rides with it, we need to unblock the interconnect.
I would say it's not clear to me that that either quantum or optical computing are ever going to reach the kind of scales that electronic switching and computing and everything does today.
For some problems, I see it like anything chance-driven. The reason why it's very appealing for AI is that any chance-driven statistical computation is a little bit easier to do with something that has a quadrillion states at any given time. But harnessing that into an algorithm that actually makes sense and spits out answers.
Yeah, I'm interested in your take about the thermal design power of the chip, because it's been like growing exponentially, and you only have such a limited surface area to apply that much power. Do you think we're going to reach the limit of how much power you can pack in the chip, or it is like going to keep going, and one day we're just going to have to figure out how to even figure out what else can we do to cool this thing down? Or there's such technological shift that you can just, totally cap it at some point, but you still can keep the compute going.
I'm not seeing at this point that 2D, 2.5D systems are going to get beyond the capability of relatively conventional cooling technology to cool them, cold plate technology, for instance. I think where things get more interesting is when we really start going 3D in terms of logic, and I foresee that happening. And then you have some linear increase additional above that, and then you've got to figure out how to cool a 3D device. And I think things will get really exciting then.
So yeah, but the thing I thought you were going to build on is what Drew said earlier, right? Like, are you going to build the singularity of compute and try to make it bigger and denser and cool it and go 3D? Or are you going to redesign your architecture to say, it doesn't make sense to try to cram more into this, let's distribute it, get a more power efficient communication strata going, and then distribute the compute out. And invariably, the algorithms have shifted left, right, and center on that, right? Everything was training was all like, who cares about latency, just get bandwidth, who cares about power, just distribute it. Inference has gone the other way. Now, if you think about inference itself, right, like 5 years ago, if somebody asked you about inference, you would have not ever mentioned LLM. It was something completely different. And the problem was getting the data efficiently into the compute. Today, it's about compute density because that's what a transformer model fundamentally does. A new algorithm might shift that again, right, in a few years. But the thing that is clear is that inference serving joules per watt per user, or joules per flop per user, is a thing you have to address. Now, how you do it? You can distribute, cut, slice. Obviously, we can't break physics, right? People are trying, but that's not going to happen.
From a capability perspective, I think there's still some room to go. Yeah. With traditional cooling capabilities as well, the cooling is pretty, prominent now in data centers. I think immersion came along, had certainly a lot of promise, to even push the PUE ratios, as we like to use the term, closer to 1. But then we ran into generic use case, environmental concerns around immersion and so on that need to get solved first before it gets largely deployed. So there's room in terms of to push the TDP up further a little bit more. But I think longer term, as we've heard, disaggregated solutions is probably required. So disaggregation of memory, disaggregation of compute, and I/O to tie them all together is where we see the path.
I would say there is some room for optimization in the device itself, but it's not factors, right? So I think maybe 2x would be at the high end, but there is room to redesign these architectures, focus more on power efficiency, and eke out more power gains. And I do feel, with as these new areas take off, people forget about that and kind of go focus on the performance side. But as things stabilize, I do expect power to drop on a per device basis. Yeah.
Great. We'll end here. Thank you, everyone, for a lively and insightful conversation. Appreciate your time.